Welcome to part 7 of our Cornucopia ML Quick Start training. This 7th of 8 videos continues the exploration of the first workshop, which was started in the previous video, number 6. Please visit our website at boditech.com for additional details on downloading the accompanying PDF course notes and other training files. Again, this is the 7th video in the course, but we are picking up partially through workshop number 1, which was typical shock Excel processing, which had been started in the previous video, number 6. All right. So if we look at this data, even though somebody might have tried to zero everything out before the measurement, we can see it's not truly zero. You can clearly see it here, especially if I zoom in. The zero line is here. The data is not really truly zeroed. So if we were to integrate that, we would get a distortion. We want to remove that out of the data. I'm just right-clicking to put that back. If you wanted to see something like this a little better, if we get out of the zoom mode, we could right-click here. We could pick Cornucopia tools, like we could pop a copy of that out. So we're not popping the instance out. It stays. We're popping a copy. And then we can make it nice, full screen. We can look. We can do a lot of things. So those are some of the things you would typically do with the Cornucopia tools. All right, so the next thing we're going to do is we're going to go and just remove the nominal offset that's in all the data. And we're going to do that using a function that Cornucopia has. So let's make another carriage return here. Okay, so what I'm going to specify, and let me just make some blank lines here so this moves up on the screen for you a little bit. All right, so to adjust this, we're going to claim we're going to take the raw data and we're going to compute an adjusted version. And Cornucopia has functions that deal with offset. The original function was called k offset adjust. It later got renamed to k offset adjust y, but to not burn people who had earlier versions of Cornucopia, the old function's left. If you try to use it, it will warn you and tell you to use the new function. So that's what we're going to use, the new function. And this new function has the following arguments. Open this up here in Quick Help. And what it wants is your data, either x and y separately or x, y together, and then an offset region n value. What it's asking for is, starting at the beginning of your data, how far should it go before it kind of puts a little cut, and it says it's going to take that section up to that point, compute its average, and then subtract it from all the data to remove a y offset. So for our data here, the trigger was 0, but the data actually started a little before that. So we're going to use as an offset the end value of the offset region to be -1 millisecond. Right here, -1 millisecond, which would work for all the different data curves. So when we go to type that in, we're feeding in our raw data, skipping the second argument, and now we put in -1 millisecond. So if we do something like this, we try to evaluate that, MATLAB is going to complain. MATLAB's going to say, I don't know what the variable ms is, because we did math here. So we could do one of two things. Up at the top, we could put in a k units variable statement, which we haven't put one in. We could do that. Or we can kind of cheat, so to speak, and we can use the fact that Cornucopia will properly interpret strings as k unit data types because it's a k unit compatible data type. The basic thing that's going on here is when you call a Cornucopia function and any of the particular arguments are expected to take k units like things, it will always call internally k units on that argument. So if it's a k units data type, it's fine, it's already compatible. If you put in a string, it'll turn it into things. So putting this in here internally, what Cornucopia is going to do, internally what Cornucopia is doing on that argument is it's doing this. which turns into a K-units entity. So this is perfectly fine to do that with. So when we do that, we will now have the adjusted data. And for the adjusted data, each of these three columns will be mean subtracted. So their initial value is now approximately 0. It's not going to be perfectly 0 because there's a little bit of noise. But when we make the plot, which we're going to do in just a second, you'll see it looks a lot closer to 0.
So Ted, that function only operates on the dependent variables in the data set.
Yes, correct. And that's why it was renamed to be offset adjust y.
Okay.
Which is meaning dependent, not as in this happens to be the column name y. But the original one without the y, that wasn't evident what it was offsetting the adjustment on. So that's why it was renamed. Yep, good question. All right, now I'm gonna make those plots, but instead of making all these commands like this, I'm gonna tighten it up and use a for loop and show you like how one would do this kind of plotting with a for loop. So before we make the plot, we're gonna just go up here and we're gonna steal this, copy that, because that's gonna tell us we want to be in plot number 2. And this is going to be adjusted data, or whatever name you would like to call it. And we will steal the bottom couple things because we're going to have it still make all the plots look the same, and we're going to have it display the plot. So now in the middle is the act of making the plot. So this time I'm going to demonstrate the concept of using a for loop. So I'm again going to use this concept of toPlot. Another benefit of using this approach of setting your variable to toPlot and then feeding that variable into the plot command is when you open up many Cornucopia examples, not all, but many, and you want to steal a little bit of code from it to put it in yours, they often will use this approach. That way you can just grab the plotting part of the commands, plunk it in, and it'll just work. So there's some overriding logic to this. Now, I want to loop. When I go to make the plots, I want to loop and have it plot this one, then this one, and this one. So I can loop with counters like 1, 2, 3. I can also loop feeding in column names. So when I made these plots up here and I referenced the dependent column as the Y column in the data, I could have put in the number 3 here. I could have put in 3 because Cornucopia will work with the traditional MATLAB-like referencing to arrays, which are numbers, or the column name referencing, which is unique to Cornucopia. So you could do either way. So here, I could reference the column names with just, or the column numbers, the 2nd, 3rd, and 4th. But what I'm going to demonstrate is referencing it by column names. The reason I like to do that is when I come to look at this code later, next month, 3 years from now, it's really easy to follow. Or if I give it to somebody, it's a lot easier for them to understand what I'm doing. If everything is referenced by numbers, it becomes hard pretty quickly to figure out what somebody's doing. So now we're going to make a for loop. I'm going to make my loop counter BQ. And I have 3 columns that I want to plot. So I'm going to go from 1 to 3. So I'm making the basic for loop, and now I will fill in. So what do I want to do here? I'm going to issue a subplot command. So this is just like I did before, except for now, I'm not going to put in physically 1, 2, or 3. I'm going to put the counter number in. And since I still want it to show up starting over here in this 2nd spot, I don't want the plot to show up here because I'm constantly going to be leaving this to put commentary in this particular example. So what I'm going to do is I'm going to start the plot to start at the counter Q plus 1. That'll start it in the 2nd spot. And I still need to put the parent command in so that the subplot goes where I want it, which is now in the 2nd tab, which is now this current tab H. So I keep reusing the variable current tab H That allows me in realistic workflows to copy from one section to the next, and everything just works nice and clean. And I need to do my little temp thing here. And now that I've made the plot, and again, I could have chose to make this Bob, Fred. There's nothing magical about names on the left. So temps just tells me when I go look at this later that that was a temporary variable. And I'm now issuing the kplot command like I did before. I'm still putting in toPlot. All right. Now I could keep typing, or I could say, hey, I'm kind of like repeating myself. So I'll go up here and I will just copy. Because while I like scripts, I'm not one to want to type if I don't have to. So I'm just putting in the same thing. So I'm pointing the plotter to the data, skipping the second argument, and now just tabbing this over so this looks nice. And if I wanted to help this be a little readable, I could put a space here. Now for this dependent thing, I don't want it to be hard coded in. I want it to go grab the column thing that we're looping through. So I'm going to say cols curly q. So cols is a cell array. Let's say that q was 2. Cols curly q would yield back what's in there, the string y. If I did it with a smooth parentheses, that would yield back a cell array, the second element in the cell array form. So that's why we're using the curly brace to step in. Okay. And maybe this time I don't want the little tiny things. I only want the major grid. So I could do something like this. And then the grid will only have the big major lines, not the extra small little lines. Now, if I still wanted the text of the peak and stuff, I could go grab that, copy, paste, and just tab this over. So, whoops, I'm hitting the tab key. MATLAB will also use the tab key to align in the text editor of MATLAB. So we're doing all this the same, except for right here. I don't want that to be the hard-coded Z. I want it to be the particular column we're pulling out. So that's a particular column we're pulling out. And now if I do that and loop around, it'll produce all the plots. And then this will take the cell array of the plot pointers and it'll match all their limits for us and then show us the slide. So we run that. And I bring this over. So we were originally here with the raw data. And so we pointed the plot to what was at the time the second tab, but it's been renamed. And we now have our data. And now the data all starts at 0. So this will be helpful when we go to integrate. We won't have a 0 shift distorting our integration for velocity data. Now, at this point, most people would look at this and say, wow, these are pretty similar shock levels. Maybe not. That, as I have stated many times in former other courses, transient data like this, the peak time domain value is of very limited use. We need to understand duration and response sensitivity to natural frequency. So that'll ultimately come out when we start to look at the data. But first, we're going to do a Fourier spectrum to understand what is the frequency content in these 3 signals. So we're going to make another section. And we're going to compute DFS. And this was Y offset. I will make an additional point. When you go look at the actual solution I give you, it might be slightly different in a couple of things here. I'm trying to give you different flavors of the Cornucopia capabilities. So the key point here was in this section, adjusting the data was literally just one command. And then this was all to make a nice plot that's all automated. You could have made this maybe with a few less commands and made everything hard-coded, but then if you read in another data file, it would be a mess. With this approach, you could read in another data file or 5 of them and process them all very quickly. Okay, so for the DFS, we're going to compute the DFS of all the signals with Cornucopia's DFS function. So a DFS function in Cornucopia computes what some people will call an FFT. It's more properly called a discrete Fourier series. And it's answering the question, what sign components is your signal made up of? So we're going to feed in our adjusted data. Now, if we had done some manipulations and our data for some reason had a non-constant time increment, this function will give you an error telling you to regularize the data. So that will occur if you are working with simulation data and you didn't regularize it. This test data here came at a constant sample rate. We've already checked that. And so we're not going to get an error. I just bring that up for those who are simulation users. So the DFS function says, give me the data, either XY format or XY together. Tell me the window name of the string name of the window you want to apply for Fourier spectrum analysis and what you want to return, which is either the magnitude or the coefficients, and then it has advanced options. So we're going to compute this with the default options, and we'll just use a simple Han window as our windowing function. And you can always try various windowing functions to see how it affects your answer. Some cases it won't affect it very much. Others it'll affect a little more. It depends on the nature of the problem you're working. So now we want to go make a plot of this. So again, I'm not a glutton for punishment. So I'm just going to go steal all this, copy, paste. Now, if somebody is looking at this like reading a book, they say, oh, wow, and all those lines I got to write. No, you don't have to write any of them. I did copy, paste. Now I'm just going to change a couple things and we'll be good to go. So maybe we'll call this Dfs Plots. So I'm going to do the same thing. I'm going to loop through the same columns as I did before. All right, so I'm going to first plot this like this. Now, toPlot isn't going to point at ADJ. toPlot is going to point at DFS. And I'm not super concerned about the peak value, so I'll remove that. And other than that, I'll issue this plot, and then we're going to make a few things. So right now, the plot, I didn't do anything special with scale, so it's going to plot in a linear style, which is going to produce a spectrum plot like this, which is not super helpful. We'd much rather have this be a log-log plot. So I could right-click on here, go to plot attributes, go to scale, and say, hey, make that a log-log plot. And then I could get that. I'm going to show you how to do that directly so you don't have to go on each one and right-click and do that. So the way we do that is with the scale option. It's an ADV option. You could find out about that through the help of the function itself by doing the tutorials that talk about plotting, or by doing the ADV variable and then scrolling at the ADV options to see if anything looks like might be something you're interested in. Now, instead of just having like the thing be log and this and that and the other thing, they're all part of a thing called scale. And under scale, you can make a linear plot, which is the default, log, semi-log X, semi-log Y, or 4CP. The 4CP stands for 4-coordinate plot. That's used when you do PVSS, shock response spectra calculations. We will do one of those at the end, and we will use that to make the plot look nice. So now I've just regenerated the plot for that purpose. And we will rerun this really quickly. And we have an error because I picked 4CP instead of log. That was a mistake. I want to pick log. When you get an error like that in the plot, MATLAB will present a result like this, showing you that there's some issue in the plot. Actually, that's a cornucopia generated error. Okay, so we'll try that again. Now, normally when you make an error like that, it's a good habit to type home so that when we recompute, we don't see an error and we don't get confused. Do we have an error or not? And I'm typing home here constantly and not CLC, which would clear this and empty it so that I have the ability, if I ever need to back up and look at stuff that I previously had echoed. So that's why I would suggest we use home. So here's our data and our plot. Usually in a log plot, it's nice to have the minor scale too. So we'll do it one more time and we'll get rid of this and we'll put it back to major and minor. So we could either do this, we could do this, or we could leave it at auto, or we could totally get rid of it. If we get rid of it, its default will be auto. In the auto setting, when you have a log plot, it's automatically put those on. So I'll just get rid of it so that we don't have extra code for no reason. And now the plot occurs more like one would expect with a log plot. Now on this log plot, you see this spike here. And knowing the accelerometer that was measured, the data was measured with, I know that this spike is from the resonance of the accelerometer. So I'm going to add into the script what that is, and then I'm going to have it put a line here and show that it lines right up with that spike. So for the accelerometer that we used, I know the sensor resonance was 200 kilohertz. If I type it like this and execute it, MATLAB's going to give an error because MATLAB's going to say, I don't know what the variable KHZ is. So I can either go put a K units variable type up there and put KHZ into the workspace as a variable, and then that math would work. Or I can just go like this. And now it's just a string, and then I can use it. Now, if I do that, the problem with that is I also want to put in this command, FC equals 0.1 times FN sensor. Because I'm going to ultimately show where my cutoff frequency is going to be, which is going to be at 1/10 the sensor's resonance. If I type this like this, and MATLAB will view that as a string, this is not a cornucopia statement explicitly. So MATLAB knows what 0.1 is. MATLAB knows what the multiplier is. And MATLAB currently thinks this is just a string. So MATLAB will do normal MATLAB math on this, and you will get FC happily computed as this bizarro result, which is 0.1 times the ASCII equivalent of all these characters, which is not what we want. So in this particular example, what we would do is we would go back to doing this and then say, oh, we ought to make this be an actual variable that we can compute with. So then I might go up to the top of my stack. Oops, wrong, K_units variables. And put in that. Now, a traditional MATLAB user taught in academia would hit the run button and they'd have clear all up here and they'd hit the run button. That's kind of an inefficient approach. You don't have to do that. We can just execute this one component here. Now the variable KHZ is in there. We don't have to rerun everything, reread the data file, anything. We can go back to where we were. And now when I execute this, MATLAB will happily execute that. And then this will happily execute as we would expect. And now what I want to do is I'm going to add 2 guidance markers to the plot. The guidance values are the keyword xguide val and yguide val. So xguide val would be guidance markers that are on the x-axis, they go vertically up. Y guidance things are on the Y axis and go across. So we're going to put on here that we want to put FC and FN sensor as two guidelines on our plot. And this value here is a value we are getting from a data sheet. It's not exactly explicitly the one for our specific sensor. It's an approximation. Let's see how good the approximation was. So we have 3 instances of this sensor, and their resonance are pretty close to the nominal data sheet number of what the resonance normally is. And 1/10 is down here, which is where we're going to set our cutoff frequency when we do a filter on the data. And we will filter away the resonance that's adding significant. And in fact, on this data set, the resonance is bigger than any other component in the data, which means once we filter away the resonance distortion, the signal and the time domain will look very different. So that leads us to now our next piece, which is the low pass filter. So now we're going to low pass filter the data. So for our low pass filter, we need to define the filter coefficients. We're going to use a low pass Butterworth filter. We've already defined the cutoff frequency up here. So we're going to define our coefficients. Normally we would use the variable C. You can use any variable you'd like. And Cornucopia has functions to do a FIR filter. Oops. So they're both under C. So there's C FIR. That would be a finite impulse response filter. Most of the filtering in Cornucopia is not done that way. We generally use an IIR, infinite impulse response filter. They're more efficient computationally in general. So that's the filter we're going to use. And that function wants to know what's the sample rate, what's the cutoff frequency, what type of filter we're going to do, and of what form. So our sample rate was FS, and we had stated that before. You can see it, it's right here. And we had computed that much earlier in the data, which was the sample rate of the incoming data. The cutoff frequency is FC up above. And the type of filter we're going to apply, we want to apply a low pass filter. So that's abbreviated LP for low pass. A high pass would be HP. And the filter type we're going to use is Butterworth. If you go and click on the help on this function, and you open up its detailed help, you would learn for the various arguments that these are the different things. And if you had a filter that was not just a low pass or high pass, but was a band stop or band pass filter, that you would be putting in 2 cutoff frequencies. But you see, you can specify this type of string into the filter. And if you were to type something incorrect, like, I don't know, Bessel. So Cornucopia does not have a Bessel filter. There is such a thing, Cornucopia doesn't have one. You would get an error like this, and it would tell you exactly what you should be putting in to the 4th argument. So we're going to put in butter, the Butterworth filter. We don't specify the order by default. That is set as the 6th order. If we want to change that, that's an advanced argument. If I scroll down a little bit farther, we can change the IIR filter order. Its default is 6. Okay, so we've set our filter. This is going to compute the coefficients. Now all we have to do is filter the data. So we'll say that that's going to be called filtered. And we're going to use the Cornucopia filter function. And what are we going to do? We're going to feed in our adjusted data. And we're feeding it in just like every other one in the XY format, this format here. So we're feeding in XY data. We skip the 2nd argument, give it the filter coefficients and how many passes. So we're feeding in our filter coefficients. And now how many passes? So if we do 2, you have a choice of 1 or 2 or the word bidirectional. Bidirectional means it's 2 passes. So that's filtered forward and filtered backwards. That was described in the training that I gave in DSP Essentials. So that computes our filtered result, and now we're ready to plot. So let's just make sure that that works fine. That works fine. Just move this up for us. For those who are interested or curious, filter coefficient is an array of numbers. Interpreting any individual number is, you have to be very deep into filter technology to know what any given number is. This is a cascaded filter, which means it's in stages. And Cornucopia's technology handles all that for you. Our filtered result is right here. One of the things that's really nice, we have done very little data handling. Cornucopia is keeping our names, our descriptions, even the user data. That's all kept there. If you want to know where this ever originally came from, that's where it originally came from. All that stuff is automatically handled by the software for you. All right, so now we want to make our plot. So let's go make the plot. And again, we just go up here and copy what we did before. We're going to go on to the 4th page of our notebook. And this is going to be filtered. So this is now what we're plotting is the filtered stuff. All this stuff keeps the same. We don't need this. But it would be nice to have the peaks back. So we'll go copy the peaks stuff from before, and we can just plunk it right in here. And I copied the wrong section. I copied the section from plotting the DFS. We really just want to copy this section here. Just do this. Because this plot's going to look just like the adjusted data plot, but except for we're plotting filtered data. So let's plot that. So that's our filtered data. Now, we can right-click on any plot and get tools to plot them out. We can also right-click on these tabs. So I could right-click on the adjusted tab and say, pop out a copy of that tab. And then a copy of the tab will be plopped out. I can make it a little bigger. I can move this over. If I had 2 screens, viewable in Zoom, this is generally what you would do. You'd put one on one screen and one on the other. But now I can look and compare the data before filtering, the data after filtering. Once I click on the filtered data, there we go. So what do we see? Well, this signal looks somewhat similar. It's a bit different here because of the filtering, removing the resonance of the sensor. But these signals look wildly different. What you were observing here was mostly resonance of the sensor, which is not the physics of the environment that was measured. Once we remove the resonance relative to the maximum bandwidth of the cutoff frequency we use, which was 20 kilohertz, this is what the real environment is. It's not this, it's this, wildly different. And you can pop out as many of these things as you want. After you've popped it out, you can further pop out plots or whatever you want. It's very flexible that way. All right, so the last 2 pieces of this example is to do velocity checks and then shock response spectra. All right, so let's go compute the velocity. The velocity, when you drop something, you start with the potential energy, mgh, the mass, gravity, the height you're going to drop it. And when it gets to the bottom of the drop, that potential energy has been turned into kinetic energy, which can be represented as 1/2 mv squared, m being the same mass as before. Manipulating those two, you can then determine that the impact velocity would be the square root of 2gh. And if the thing comes and hits the ground and stops and doesn't go anywhere, then the change of velocity is going to be the square root of 2gh, because it's going to go from that to 0. If it rebounds with perfect elasticity, has a coefficient of restitution of 1, then it would rebound with a velocity going the opposite direction, the same value. So the total net velocity change would be twice the square root of 2gh. So we can use those numbers to help validate that the acceleration data we just measured is real and proper. So first thing we need to know is how high do we drop it from? So we know that from a couple places. One, we see it here in our thing, and we got that from the header from the text, from the original data file. That's also, so we could go extract it off of this, or we can extract it off of the header text. So, but since I have it here, it's easy to see, I will use that. So if I type just here in the command window, raw.props.description, see we get a cell array. And MATLAB parlance, if I say, give me the end of that, it's going to give me the end component of the cell array. It'll give me this last one. And since I did curly braces, it'll give me what's in it. And I will get this. So I want to turn that into a value. So I can do that very nicely with the unpacked header function as before. So let's compute the unpacked header function. So the drop height, we're going to use the unpacked header function. It's right here. And again, I'm using the tab continuation from MATLAB to get these lists. So with the unpacked header function, I'm going to say, I want you to unpack that value. That value is this string. And the beauty of this is Cornucopia will turn that. Oops. I didn't complete the second argument, which is what is the delimiter between the values and something that you might consider to be a column header. So in this case, it's an equal sign. All right, so now if I execute that, let me re-echo this so you can see. Oops, 1 second. So there was the end. And now the unpacked header has turned that into a variable that I can compute with. So I want to go compute delta V. This is going to be like a theoretical bounds. So the theoretical bounds are, it could be anywhere between the square root of 2 times G times H drop, or 2 times that, based on the description I had just given a minute ago. Now MATLAB is going to complain that it won't know what the variable G is. And I've one too many parentheses there. Okay, it was giving me a little red error there. That was because I had one too many parentheses. So when I do this, MATLAB's going to complain, I don't know what G is. So we can just simply go back up to the top. We can add G to our list of units variables. So now there'll be a variable called G. As long as we haven't used G for something else, we're good. And now it does this calculation. And as I showed yesterday, when you do math and you're multiplying, you have things with different names and column names, it's not necessarily obvious what the final output column name should be. So Cornucopia is warning me when I did this calculation here, and then when I repeated it here, it didn't know what to name the output for a column name. It still computes it. The answer is still there, but now there's no column names, there's just units. So if you do a lot of these kind of calculations, this will become annoying. So you might click here to have open up the help and learn about it. And you'll see, oh, this is how you turn the warning off. So I'll just copy this. I'm copying that. And then I would go back up to the top of my file. And I would put that command in there. So kset is a Cornucopia function that sets global Cornucopia behavior. It's not global value, variables that are seen. These are variables you don't see. This is behind the scenes, but it sets global like behavior in Cornucopia. And so by doing this, we're going to turn that warning off. So I'll execute that. And if I go back down here to the end, and I type home, so you can see that now it won't show up, and I recompute this, no warning shows up. So in the actual solution, you'll see that that sits at the top of the script to turn off that kind of warning. The warning is helpful when you're very first beginning to use Cornucopia, but most people will quickly find it to be kind of a nanny cam, an annoyance, and most people will want to turn it off. All right, so we've computed our theoretical bounds. Now we need to actually compute the actual velocity itself. So we have accelerometer data. If we integrate that, we can get the velocity. So I'll say that the velocity is going to be k underscore integrate. And we also have a k underscore derivative function that does a very nice, accurate polynomial-based, spline-based derivative technique that's very, very accurate, much more accurate than the diff over diff approach that you would find if you Google how to take a derivative. And this integration is more accurate than the default MATLAB integration function because this also uses a splining technique. So when we integrate our data, what are we going to integrate? We'll integrate our filtered result. Here's our filtered result. Now, if I open this up, the integration, if we're doing the second form, we're given the XY data together, we would skip, and then we would specify initial conditions. So we could either do some elaborate assessment of what we want to put in as the initial condition, which we could say is this free drop velocity, and then we would have the true velocity. Most people, when they're doing this kind of shock data, what they're really doing with this velocity integration is looking at the change in velocity. So you normally wouldn't specify an initial condition. So if we're not going to do that, we can just literally go like this and specify no additional arguments. And then this will really be the change in velocity of the response from the accelerometers. And so now we want to go and make the plots. So we'll just take the same plot that we had from here, copy this, paste, and change this to sheet number 5 in our notebook. So this is velocity. This is going to be the velocity. And we'll loop through, we'll be making the plots. We don't care about this. But what we would like on the plots is we would like Y guidelines that show the two bounds, the upper and lower bounds here. So we're going to put in Y guidelines, which are called Y guide vals. And we're putting in those theoretical bounds. And now when we issue that plot, we would get a result like this. Now, in this particular case, we're plotting all three of them separately. So let's change and not do it separately, but let's go and put them all on one big plot in this one figure window. So I'm going to go back, and instead of looping all that stuff, I'm going to slightly change this behavior. We're just going to make it a one big plot. I'm just making it still line up nicely. So the velocity, right, automatically already has our columns. So I can just feed that in. I don't have to specify any dependent column, and it'll automatically loop through all three columns and put the plots on. It'll automatically put a legend on. And I can literally get rid of all this and just have it all on one big plot. And I have one problem. I made a plot, nothing appeared to show up. Because I did not use a subplot before this, it doesn't know where the parent is. So I go here and put in the parent command to put in the current tab. current tab H, current tab H. If I reissue that, I get the plot, and I have this guideline here. The other guideline is not showing because it's up here somewhere, so we can make and change the axis to show that. So what I'm going to do is I'm going to change the Y limits of the plot. Now, I could put in K variables as an array, or I can just put in a string. So what I'm going to put in here for a string is, if I look at this plot, I can say maybe I want to go from whatever it is by default in the bottom, which would be setting it to -infinity. Now, if I just do this, and let's say I want the plot to go up to, let's say, 8 millimeters per second. If I do this, Cornucopia is going to give me a units error. It's going to issue an error. And it's going to say, we have a problem with this. There's incompatible units because you didn't specify any units with this. So what I need to do is do this. So I could do that like millimeters per millisecond, or I could say meters per second. That's the same. There's 1,000 on top and bottom. And now when I issue the plot, that will work. And now I have my upper bound, my lower bound, and the values. I could additionally add text to show up where the upper and lower bound is. That's described in the actual solution. For brevity, I'm watching the clock here. I will skip that extra bit of code. Actually, I'll just paste it in real quick. I won't type it. Let me just add that just to show it. I'm just pasting this in from the known solution I have. So what I'm doing here with this figure function, displaying on figure, I'm displaying on the plot we just created. I'm displaying at x equals 0.2%. So, or not 0.2%, 0.2 in a normalized space. But in the y direction, I'm specifying an actual value. And I'm controlling that with this location unit saying I'm giving mixed, normalized, and then data input. And I'm doing the same for the other bound. So now the plot ultimately looks like this, with some descriptive text of the two bounds. All right, the very last piece of this example is the computer shock response spectra. So we'll do that really quickly here, and then we will save our figure, create a PDF, and take a break. All right, so our last thing is shock response spectra. In the actual solution, I demonstrate computing it before filtering and after filtering. For brevity, I'm just going to demonstrate the filtered version. I'm just going to call it SRS. Okay, underscore, so the function's SRS. And like before, we give it XY data. We can give it separately, or we can give it all together. And here, it's renamed as T and A because for shock response, you can't give generic X and Y things. You can only give time and acceleration. So we're going to use the second form as before. And we'll hold this up over here. And we'll feed our data in. So we're going to feed in our filter data. In the second argument. And now we need to specify a minimum frequency, natural frequency for the shock response spectra, and a maximum. So typically the maximum will be, we will use to be set based on the code itself. And the minimum will be something that we think is reasonable for our problem or our data. In this particular case, we're going to set the minimum to be 10 Hertz. And the maximum will enter into the function itself. And we'll set the damping value to be 0.05, which is kind of an often used default kind of damping value. So then we're specifying it's filtered. We're going to go for the minimum. And then if we put this as a string, oops, not a variable. This is a variable, points to this. This is not a variable. This is an entry. And what we're telling the software here is you figure out the maximum frequency, natural frequency that this SRS can compute given the sample rate of the data. And we let the software do that for us. You could put similarly FN min here and let the software pick that. You'll often get a pretty low frequency. And the lower you run frequencies and shock response, the slower the calculation. So usually you will override that and put something in that you think is appropriate for your data. Okay, so then we're going to add the damping, and the type of shock response we want to specify is the PVSS. So if we do that, and we calculate these three, that's gone and calculated the shock response. It's appropriately labeled it. It knows to label the x-axis to be the natural frequency axis. And now we want to make a plot. So the shock response plot is somewhat similar to a DFS plot. So we'll kind of steal the DFS code. Except for here, we're not going to loop. So actually, instead of stealing that, I'll steal the non-looping velocity plot. Because we're not going to loop, we're just going to plot this in one large plot. So the plot that we're on is, we're going to plot this in spot number 6. This is going to be our SRS variable. And we're not going to control the limits. We're not going to put any bounds at the moment. We are going to change the scale. So this time, instead of using the ADV variable, I'm just going to directly put in 4CP. Oops. Could have used the ADV variable like what's done above here, or not. And once it's 4CP, there's no control over the grid because this has a bunch of grids that are automatically put on. And we will end the thing so it shows us the tab. And now we've already computed this, so I'll just highlight this part, compute it, and we get our shock response spectral plot. Now, if you want, we can take this and we can make the lines a little fatter. I'll make the lines a little fatter. That's by the option line width. And if I put a single value, it'll go for all curves. If I put an array of values, it'll go per curve. So I'm going to just make them all a little fatter. The default value is 0.5. So when we, replot that, now the lines will be a little bit fatter. So right now, the title, there's no title here. So we would like there to be a title. And if we look at the SRS variable, you can see that there's a nice title. And particularly the bottom row is an important thing that's telling us it's a PVSS with a damping ratio. So I can add that title manually here. I can do that in one of a couple ways. One way to do it is to issue the title command. These are all ADV options of kplot. You do not issue separate title command calls. So I can reference things with title, like I can say, get the title from the Y description. And I can type that short. I could do something like that, and it will issue a title based on the Y description, big long thing like that. Now that's a lot of stuff. We don't need all that extra stuff in the plot probably. If we don't want such a big long title, I can specify specifically what I want. And we do that by entering a cell array with the first word being user. That tells the software it's not going to look anywhere particular, but it's going to put in whatever I tell it. And then I could tell it here, I could tell it something like, have a nice day, which wouldn't be the most appropriate title, but nonetheless, I could do that. And now it'll say, have a nice day, or I can instead go and pick from the data and props from the description. If I pick the last part of the description, the end, the end of the description will be that last row, and I would get a title that would be appropriate for this plot. And I forgot to close the closing curly brace. And now I have the SRS plot for that particular example. Now, the final thing, and then we take a break, is we want to save this. So if we want to save this, we do not hit this button, and we do not do this, because that will save it, and it will not save all the Cornucopia stuff behind the scenes necessarily correctly. And if you then give this to a user to open it up, and they're not a Cornucopia user, most of those tabs will look empty to them. So we're going to save it with a Cornucopia menu. Before we do that, we're going to quickly get rid of the extra sheets of paper that we didn't want. So I can right-click, modify the tab, delete it, and do this for the same couple other ones. Of course, I could have went at the beginning and not put in 10 sheets of paper or 10 tabs. I could have just put in 6, like the number we're using. I'll just clean those off. All right, so I can go here and I can say save. I'll save the figure file, and this has some help about why you want to do this. This pop-up occurs. You need to basically be specifying a folder and the name. By default, it remembers the last place you would save data. So we want to save this in our working folder. So I'm actually going to cancel this because the working folder is not what I want it to be. Working folder should be here. So now I will save this. Again. So I can browse around, or I can say, just do it from the working folder, present working directory, and it'll set that where we are. And then I can type in whatever I want the name of the figure to be, including the extension, or I can specify, as stated up here, the special minus fig name.fig. If I do that, the software will go and look at what is the figure name, and it'll replace here what the figure name is. So then I save it something similar to the way I name it, so that if I open up multiple ones of these, it's easy to know what I'm looking at. Now in this particular case, I already have that answer here. So I'm going to just slightly change this. I'm going to put _2. And now it says, hey, your name is different for the file than here. Do you want to change the name up here? So I'm going to leave that alone for now. I mean, I could go and say _2 if you want. Make it consistent. And now it's going to go save the figure file. A little window that's yellow will pop up saying, don't touch anything, while the software goes and gets all the Cornucopia stuff straight and saves the figure file. Now I have the figure file saved. Now I want to share it with my manager who doesn't have MATLAB and Cornucopia, so I'll generate a PDF. Again, I will start from the present working directory, and I will use the same negative fig name, but this time it's a PDF, and it will automatically pull that name down for me. And then it gives me an ability to put some other stuff for the title page of the PDF. So again, I'll tell it to go grab it from the figure name. And I can put a subtitle if I want, you know, my workshop. And now when I say OK, what's going to happen is it's going to take screen grabs as it walks through all the tabs in the thing, and then it'll assemble those into a nice PDF that you can share with anybody. This is way faster than grabbing all those things and individually copying them into a PowerPoint. And if you spend the time when you make the plots to add comments, you have basically a nice report that's all done, ready to go to be shared. The first page will have links to all the particular tabs and whatever you had put as the header information. And then you can literally go page by page and look at PDFs of the stuff. So had I spent a little more time, I would have had commentary here. And then this would basically be a finished report that I could give to somebody. That concludes the first workshop and part 7 from our Cornucopia ML Quick Start training. Please continue with the next and final video for this course, part number 8, via the link provided on our website. This final video will cover the second workshop in the course, cleaning messy tension data.